Okay. Good morning. So I wanted to kind of build on what Jenny talked about, this idea of putting complicated things inside your data frames, and talk about one specific instance of that, where putting models inside your data frames, I think, is a really, really powerful idea. So how many of you have seen Hans Rosling present before? So you may have seen one of his fantastic animations where Hans Rosling talks about kind of how the world has developed over the last 100 years. And he is an incredible and dynamic speaker. And so if you've never heard him speak about data visualization before, your homework for today is to go and watch him talk. Now, so he presents these amazing, incredible visualizations. Kent showed you some awesome interactive visualizations as well. I instead am going to show you some really boring visualizations. So this is a line plot showing exactly the same data as what you just saw in that animation. So here we've got 142 countries. Each country is a line, and we're seeing on the y-axis the life expectancy and on the x-axis time. So what we're seeing here is kind of how has life expectancy changed over time for 142 countries. And this is not just like small data, this is like tiny data, right? There's like 1,000 observations here, like 3 variables. This is really, really small. But as you can see, even with this amount of data, it's hard to see what's going on in a single plot. So to kind of tease apart what's going on in this data, and with many data sets, I think it's really useful to use modeling so you can extract key patterns that maybe you know about already, so you can look at what remains. And so what I'm going to kind of walk you through today is to go from this raw data to this visualization, where now each point is a country. And what I've done is I've fit a linear model to each country. On the x-axis, you see the R-squared, some measure of model quality. And on the y-axis, you see one of the coefficients of that model, or how much is life expectancy increasing on average or changing on average for every country. Now, I think this is a really interesting plot, because now we can start to see not just kind of the individual path of each country, but we can start to see how countries maybe move together or are similar or different. And then if you look at this plot in particular, you can see that there's a whole lot of countries. We've got some countries that this model fits really, really well, right? We have an R-squared of like 0.99. Which is basically like so high, if anything, you're suspicious about the data. But we've also got a whole lot of countries that model does not fit well. And you'll see all of those countries have something in common. They're all African countries. And so as we work through the analysis today, we'll see some reasons for why that is. So I'm going to show you this idea on this very simple data set, this very small data set. But I think it's a really neat series of techniques, because it can handle arbitrarily complex models. It scales very, very naturally to much, much larger data sets. And there are 3 simple underlying ideas that you can apply in other areas of your work in R as well. And so there's these sort of 3 ideas. Jenny's talked a little bit about the first 2, but the first of all, this idea of list columns. And I'm going to talk about a particular type of list columns, which I call nested data, where we're going to do something a little crazy. We're going to have one column of our data frame that is a list of other data frames. I'll talk about this in more detail. It took me a while to kind of figure out whether there was this like insane or was this a really good idea. I think it turns out to be a really good idea. And then as Jenny talked about, like once you've got these crazy list columns, how do you work with them? It turns out that the tools of functional programming like map and map2 are really useful. They allow you to express very naturally complex operations on this type of data. And then finally, we'll talk about like once you've got these models, how do you understand a model? And I think a really useful way of dealing this is to take your data, take your models and turn them into tidy data using the broom package by David Robinson. So I'm going to focus kind of on so Jenny gave you a flavor, I think, of why you should learn functional programming. It allows you to express ideas. It doesn't allow you to do things that you could not do before. You can't do anything with functional programming that you couldn't do with a for loop. But I think in general it allows you to express things with more ease. You can write less code, and writing less code is always a good thing. So I'm going to talk about these ideas of nested data and then turning these lists of data frame, list of models into things that you can then visualize. So we've got these 142 countries, and what I want to do is fit a linear model to each country. And if we're going to do that, it's going to be really useful to have one data frame per country, because that's kind of the input to a model, right? There's two main inputs to the model specification or the model formula, and the data frame. And so what I want to get to is I have 142 data frames, so I can fit 142 models. And so this is what the data looks like. Again, here I'm using the Gapminder package from Jenny again. And this is what the data looks like. We've got a row for each country for each year that tells us what the life expectancy is. There's a few other variables in the data set, but we're not going to look at those. But if we want to fit a model to each country, it's going to be more useful to have a data frame per country. And so I think we're going to move into what I call a nested data frame. So instead of having one row per observation, we're going to have one row per group. And so now this data frame is going to have two columns. One is going to identify the group. Here we just have a single variable that identifies the group, the name of the country, and then we're going to have the data for that group stored inside of this list, inside of this data frame. So I call this a nested data frame because you've got like data frames inside data frames. And again, it took me a while, like this, I have a lot of ideas that I'm like, wow, this is a really cool idea, and I think this is awesome. And then I realized, like, well, probably no one else will think this is awesome, or it's like too complicated. And for a while, I kind of worried that maybe this idea was like too complicated. But I think it is a really powerful idea, this idea of switching from one row per observation to one row per group. Because as soon as you move into modeling, there's lots of things you want to be able to do per group. For example, you want to fit one model per group. And so this is how you're going to create that data frame in R, and I'll kind of give you this high-level overview of what's going on, and we'll run the code a little bit later so you can see there's like nothing hiding behind the curtains. But what I'm going to do is I'm going to take the Gapminder data set, I'm going to group it by continent and country, kind of lied a little bit. There's actually kind of two identifier variables it's useful to preserve, both the name of the continent and the name of the country. And then I'm going to use this function called nest. So that gives me a nested data frame. I'm going to have columns that identify the group. I'm going to have a column that has the data for that group. And now I want to fit a model to each country. Right? So I've got a data frame for Afghanistan, and now I want to have a model for Afghanistan. I have a data frame for Albania, now I want a model for Albania. And if I'm going to have a model for every country, well, why not put that in a column as well? And I think this is a really useful idea because you want to keep related things together rather than just having like vectors floating around in your global environment, because whenever you change the order of one or you subset one of them, you have to remember to do exactly the same operation to every other thing. This is, I think, when you have just vectors floating around, you get to this problem, like, which I think of like the classic Excel data analysis problem, which is you're in Excel, you go to sort your table, and instead of changing the order of all the rows, all Excel does is change the order of the single column that you've selected. And if you don't notice that, you've basically randomized your data, right? You've broken the connection. And for the same reason you don't want to do that in Excel, or maybe you don't want to use Excel at all, the same reason you want to keep related things together, you put them in a data frame, and then when you operate on that as a whole, rather than having to remember to do the same thing to every single one of these vectors that are floating around. And so if we're going to do that in R, we're going to combine together two tools. We're going to combine together dplyr, which we use for working with data frames, and we're going to use that with purrr to do something to each of these data frames. So I'm going to start just by creating a little function. This is the function that's going to take a data frame as input and return a model as output. Then I'm going to say I want to take my existing country data set and I want to mutate it. I want to add a new column, And that new column is going to be a column of models, which I fit by taking each of these data frames and applying this model fitting function to it. Okay, so I've got 142 countries. Each of those is a line on this graph. I've got a data frame where one column is the data for that line, and I've now got another column, which is the model, the linear model. And I should emphasize, this is like pretty much the simplest possible model you can fit, right? I'm just going to predict life expectancy with some intercept plus some slope times the number of years since 1950. And this is where we want to end up. So we want to be able to create a plot that shows us like how well did the model fit, and then what is the model telling us about the data. Because whenever you are trying to interpret the coefficients of the data, coefficients of the model, or predictions from a model, you always want to calibrate against that. Is this model actually a good summary of the data? So you can see here, for example, you can see a few countries where it looks like there's actually a decrease in life expectancy over time. But those models are very, very low R-squared. That's telling us, well, there's not actually a linear pattern. So you shouldn't try and interpret like some very simple summary of that pattern. We're going to need to look at the data to see what's going on. Okay, so we've got this data frame, we've got the information about each group, we've got the data for each group, we've got the model for each group. Well, what can we do with a list of models? Well, I think we need to think about, well, what can we do with a single model? And I think when you've got this data set, so here's New Zealand, for example, you fit this model. What data can you get back out of that model? I think this is the question that fundamentally the broom package answers. Given a model, what tidy data can you extract from that model? And there are basically three levels in which you can extract the data. So the first one is you can extract information about the model as a whole. So Broom calls this glance. So this is, you have one row per model, and there's basically three things here. There's measures of model quality, like the R-squared, or, well, the R-squared is the most important one. There's measures of model complexity, like the degrees of freedom, and then there are measures that attempt to trade off model quality with model complexity, like AIC and BIC and adjusted R-squared and so on. So that's glance. That gives you one row per model. Then we have tidy. So what tidy is going to give you is it's going to give you one row per coefficient, or one row per parameter of that model. So it's going to give you the estimated value of that parameter. It'll give you the standard error, the t-value, the p-value, and so on. And then finally, you could augment the model, which is to get one row back for every row that went into that model. And generally, so that's things like the residuals, the standardized residuals, the predicted values, and so on. So what I'm going to do next is I'm going to add 3 new columns to that data frame for each of those 3 possible summaries. I've got a row for the tidy, a row for the augment, a row. Let's put these in the same order, actually. So I could augment it. Those are the summaries where I've got one row per model. I could tidy it, which gives me one row per parameter, or, sorry, I did that around the wrong way, didn't I? This is why you shouldn't edit your slides during a talk. Okay. You go to tidy it, which gives you one row per parameter, or you can augment it, which gives you one row per original observation that went into the model. So now we have this. So now we've got a data frame that contains a whole lot of list columns. And so at least we've gone from this model object, which you didn't really know what to do with, but now we have a list of data frames. And so what can you do with a list of data frames? Well, I don't know. But one thing you can do is to do the inverse operation, which I started out with. So we started out by nesting the data, taking a regular data frame and turning it into this nested data frame where we now have a list. One of the columns is a list of data frames. We can do the opposite. We can unnest. We can take this crazy data frame with lists of data frames inside of it and turn it back into a regular data frame. And then once you've got that, you can do everything you're used to. You know how to work with a data frame already, right? That's what you spend most of your time doing in R. Okay, so that's kind of the big picture. What I want to do now is dive into the details. So I'm going to start by loading some packages, and I notice here that my favorite thing has happened, which is the two packages have exactly the same number of letters, which makes personally me happy. And that's why, if you ever wonder, like, why does purrr, you're like, why does purrr have so many R's in it? It's basically so it like lines up nicely with everything else. So you'd be surprised by how much time I waste thinking about things like this. Okay, so this is the gapminder data. It's got a few other columns than what I told you about before, but only 1,700 observations, right? This is really, really small data. This is just a toy example. But as I said earlier, these ideas, they apply regardless of how complicated your model is. And the thing that's neat about this idea, this strategy of fitting separate models to each group, is that it's trivially parallelizable. So if you've got so much data it's spread across multiple computers, each computer can be fitting models to the data that it has. You can then pull those summaries, those models back into R and work with them there. I'm going to do one little bit of mutation before I start. I'm going to compute the number of years since 1950. And that's just going to make the coefficients of my model more meaningful. Because if I don't change it, I'm basically going to be, my intercept is going to be the intercept at year 0. Right? I'm going to be extrapolating the data out like 1,900 years into the past, which is not a very good idea. So then I'm going to nest it. And as Jenny mentioned, one of the challenges currently with dealing with these list columns is that there's not like a great way to dive into them. So the default print view gives you a very high level view of what's going on. We can see now we've got 142 rows, 1 row per country. We've got the continent, we've got the country, and then we've got this data. Now generally in R, like if you want to see a complicated data structure, str is your friend. In this case, str is not really your friend because it still prints out like pages and pages and pages of data. But if we kind of pull apart, if we like take this data set, this data frame, we pull out the data column, and then we pull out the first element within that, you can see that this is just a regular tib or a regular data frame which has the data for Afghanistan in it. So we've got this list of data frames. And we want that list of data frames because once we have a list of data frames, we can say, well, transform that list of data frames into a list of models by fitting this model. And so that's what I'm going to do next. So I'm adding a new column. So I use mutate from dplyr. I use map from purrr to say, do this thing to every one of these data sets. And so now I have this data frame where I've got the information about the group, the actual data for that group, and then this model. And the thing that's neat about this already, because we have these things in the data frame, I can say, well, I want everything to do with Africa. And I have both the data and the models. And I can just use all of the tools I'm already familiar with for working with data frames to subset them and arrange them and so on. So the next thing I want to do is to use broom to convert those models to tidy data frames. Again, the whole philosophy is like get everything into a data frame as soon as you possibly can because you use data frames all the time. You have all of these tools for working with data frames. And I think at the heart of this is there's this tension between like, do you want a specialized data frame, a data structure that is perfectly tailored for the problem at hand, or do you want a general data structure? And maybe you've got to shoehorn your problem into it a little bit, but because you've got this general data structure, you're going to use it again and again and again, and you're going to have general tools that you're familiar with, and you can deploy when you encounter a new problem. So I'm going to add these extra columns. Again, you should not do this yourself, but if you str this, it's even worse than before. That's quite bad. This is something that we're very aware of currently. I'm pretty sure in the next release of RStudio 1.1, there'll be some better tools so you can kind of interactively dig down into these complicated lists and not have everything printed out for you in one giant step. Now, the other thing I did here, I added one other column called r². I used that helper that Jenny mentioned, that I'm going to give map the name of a component, and I'm going to pull that out. So now if we look at this, and if I make my screen a little wider, you can see I also have the r² here. And again, this is cool that it's here because now I can say, like, sort it in descending order. And because everything's in the data frame, all the models in the data frame, just all the models and those individual country data frames are transformed in exactly the same way. And then I can do things like take that data, I'm going to do a little plot, I want the r² on the x-axis, I want country on the y-axis, and just give me a simple dot plot. And you're not going to be able to read the labels here, but you can kind of see what's going on with the overall distribution of the r². Right? A lot of countries, this model does a really good job, but Africa in particular, we see a lot of countries where this model does not fit well. So whenever you're doing this in your life, you're going to want to dig in and say, like, well, why is that? What's going on in these countries? And what I did is I made a little RStudio gadget with Shiny. And so here I can just look at the plots of the individual data for the countries with very poor r², with very low r². So we've got Botswana, Lesotho, Rwanda, Swaziland, Zambia. So the kind of the poorly fitting models are like all these terrible things that have happened to countries. So Rwanda, we have a civil war, genocide. Does anyone know what this big bump is? Like life expectancy is increasing in all these countries in Africa until like the mid-80s, and then it just plummets. That's the HIV/AIDS epidemic. So if we look at the kind of the next swath up, we see again with countries that are this affected in very similar ways, the HIV/AIDS epidemic, and look a little higher. And we start to see more diverse. I have no idea what's going on in Bulgaria, Cambodia, again, civil war, Iraq war, and so on. So the kind of the story, like overall, is very positive. Like most countries have had a pretty linear increase in life expectancy over time, but the few countries that have not, there's been because something's going wrong. Okay, so we've got this data frame with these lists of models, lists of data frames. Now we want to unnest them to get back to a regular data frame. I could unnest the data column. That would basically get me back to where I started. Or I could unnest the glance column, say, and see for each of these models all of the summary statistics, the r², again, measures of model quality and measures of model complexity, and then these measures that attempts to trade off quality versus complexity, like AIC and BAC. We can also extract those coefficients by saying unnest the tidy data. And so notice here that there's two coefficients in this model, so each country is going to get two rows. It gets one row for the intercept and one row for the year, and we automatically carry along all of the other normal metadata about the groups along for the ride. Now what I wanted to do here is I want to do a plot of the intercept versus the slope. Now this data isn't arranged in quite the right way, but this is a data frame, so I can use the tools I already know about, like tidyr, to rearrange it, to reshape it, so they have a column for the intercept and a column for the slope, and then I can plot that. So the advantage of picking this common data structure is that I can reuse familiar tools again and again and again. And so this plot, on the x-axis, I've got life expectancy in 1950. On the y-axis, I've got the yearly change in life expectancy. So these are the two coefficients of my model. And then I've sized the points according to some measure of the model quality, or the R squared. So you can see there are some points down here with average decreases, but we want to be cautious about interpreting those values because our model did not fit well. You want to be very cautious when you're interpreting a summary when that is a bad summary. And then we can kind of continue on and do all sorts of other plots. This one, for example, shows the residuals across all of those models. So this is a little different to the usual residual plot, right? Because normally you're looking at the residuals from a single model. Here we're looking at the residuals from 142 models. What I've done here is I've broken it down by continent, so you can see particularly for Africa there's some pattern in the residuals, right? There's some shape that our model is missing, but even in Africa in particular, we know about the HIV and AIDS epidemic, but even in the Americas and Asia, there's some indication that maybe it's not a linear pattern, but maybe there's some quadraticity in there as well. So to me, this idea of using list columns is a really powerful idea because it allows you to keep arbitrarily complicated things that are related together and work with them in unison. I think it's worthwhile to learn some of these functional programming techniques, whether it's the apply functions in base R or the somewhat more consistent family of map functions in purrr. I think it's really valuable, not because it allows you to do things that you could not do before, but it allows you to do them with greater ease and with fewer errors and with less mental effort. Finally, when you've got these models, when you've got hundreds of models, you want to understand what's going on. Really, really powerful technique is to take those models and turn them into tidy data frames. And a great way to do that is to use the broom package by David Robinson. So here's kind of the summary of how all these bits fit together. dplyr works with data frames, and purrr works with list. tidyr does lots of things, but one of the things it does provide is these nest and unnest tools for converting between the two. And then you have broom if you want to take your models and convert them to data frames. If you'd like to learn more about any of the techniques I've talked about here, the best place to go is the book R for Data Science, which I've written with Garrett Grolman. That is going to be free online forever, and it will hopefully be available in print maybe by the end of the year, or at least early next year from O'Reilly. Thank you. I think we have time for one question, two questions.
Is it possible to extend this to, so statisticians do lots of simulations, so varying simulation parameters. Do you see this as a simple extension? Because one of the problems I have is being able to gather the parameters I use, especially if you send this off on a cluster.
Yeah, absolutely. So the way that I generated these multiple data frames, multiple models, is by doing subgroup analysis, basically. But there's lots of other ways you might get multiple models. You might be doing a parameter search, or you might have generated many data sets through bootstrapping or cross-validation. I think this approach works really, really well there as well. Take one more question, if anyone's got a burning issue.
Thank you. A tiny question. I'm curious how you increment versions for the tidyverse package, since it's a collection of packages.
That is an extremely good question, which I do not currently know the answer to. I have traditionally taken the approach that managing package versions is your responsibility, not mine, which is certainly somewhat user hostile, but makes my life much easier. I think generally, it's, when you're doing an analysis, you're not just going to be using the tidyverse, you're going to be using lots of other stuff. So I think what we want is more general tools to help you manage that. I think PackRat is one step in that direction, but it doesn't feel fully there yet. It's just a little bit too much friction. I would like to get to the point where it's just so easy to do it, it's your default way, and hopefully we'll get there one day. Thank you.